Right now, something extraordinary is racing toward our sun at 36 miles per second. This traveler carries ice older than Earth itself, formed billions of years ago in a distant star system. In this story, you'll see the moment telescopes first spotted it, why its speed broke every record, and how even tiny grains of dust are reshaping what we know about the space between stars. This is only the third confirmed visitor from outside our solar system, a wanderer older than life on Earth, arriving here today. Get ready. The journey begins now. High above Chile's Atacama Desert, a robotic telescope was scanning the night sky for dangerous space rocks. But instead of finding a threat, it uncovered something no one expected, a strange object moving in the wrong direction. Our solar system is like a giant whirlpool, with the sun at the center and the planets circling in order. Everything formed here follows that flow, like leaves drifting downstream. But this object was different. It cut across the system at an odd angle, moving against the current and beyond the sun's pull. Within hours, astronomers realized they had found something extraordinary. Most asteroids and comets travel thousands of miles per hour. This one was blasting through space so fast it could escape not just our solar system, but even the pull of nearby stars. The discovery stunned scientists. If the numbers were right, this was only the third interstellar visitor ever found, after Oumuamua in 2017 and Comet Borisov in 2019. But this new traveler was even more mysterious. Unlike Oumuamua, the size of a football field, or Borisov, the size of a city block, this object seemed far larger, stretching miles across, carrying frozen material from a star system so distant its light takes decades to reach us. By chance, that telescope in Chile had opened a rare window into the deep cosmos, offering humanity a glimpse of matter born far beyond our solar neighborhood. Within 72 hours, observatories on 6 continents aimed their telescopes at the same spot in the sky, racing to capture every trace of light from this cosmic time capsule before it vanished into deep space. But the real shock was still hidden in the data, about just how fast this object was moving. Imagine standing on a highway where every car moves at the speed of lightning. That's what astronomers found. This interstellar visitor wasn't just fast, it was blazing through space at 36 miles per second. At that speed, you could fly from New York to Los Angeles in under 2 minutes. A 6-hour flight would be over before you finished reading this sentence. The numbers stunned scientists. Oumuamua had traveled at 16 miles per second. Comet Borisov reached 20. But this new arrival was nearly twice as fast as anything we'd ever seen. And speed wasn't just a record breaker. It told the story of a violent past. To move this quickly, the object must have been launched from its home system by an enormous cosmic event. Astronomers call this hyperbolic velocity, like throwing a ball so hard it escapes Earth, the sun, and never slows down. At 36 miles per second, time was running out. Unlike asteroids that linger for millions of years, interstellar visitors pass through in a flash. This one would cross our entire solar system in less than 2 years, giving scientists only months to study it. The race for data began, with every clear night and every hour of telescope time becoming priceless. Then came the mathematics that sealed the mystery. When astronomers traced its orbit backward, they found the object had crossed the galaxy for millions of years, arriving from the direction of Sagittarius. Its orbital eccentricity, a measure of how open an orbit is, was a staggering 6.2. For comparison, Oumuamua was 1.2, Borisov 3.6. This path was the most hyperbolic ever recorded. Undeniable proof it was interstellar. Weeks later, the International Astronomical Union made it official. The object was named 3I/Atlas, the third confirmed interstellar traveler in human history. But the surprises didn't stop with speed. This wasn't a small visitor. Early estimates suggested it was 6 to 12 miles across, truly massive compared to Oumuamua or Borisov. If Oumuamua was a football field, this was an entire city. Size mattered because larger objects survive interstellar travel. Smaller ones get destroyed by radiation and cosmic dust, like sandblasting across millions of years. But this giant endured, carrying with it the untouched material of another star system. Captured by Hubble, the object appeared as a glowing teardrop, a bright icy core surrounded by a halo of gas and dust. Hidden inside that glow was a frozen heart that had traveled across the galaxy, now offering humanity a fleeting glimpse into the deep past of the stars. Our visitor's sheer size meant it survived millions of years of cosmic weathering. Though its outer layers were stripped away, enough material remained to create the dazzling display we see today. Every grain of dust drifting from its nucleus carries the story of a distant star system, now mingling with our own. But launching something this massive into interstellar space takes extraordinary power, giant planets slingshotting it away, or even a stellar explosion hurling it across the galaxy. That rarity made the discovery even more remarkable. Think about it. In all of human history, with thousands of years of skywatching, we've confirmed only 3 objects from beyond our solar system. That's fewer than the number of people who have walked on the moon. Each detection is as monumental as discovering a new continent. The odds are staggering. Our galaxy holds over 400 billion stars, many with their own planets constantly ejecting comets and asteroids. Countless wanderers must pass between the stars, yet most slip by unseen, too small, too faint, or in parts of the sky we're not watching. Spotting 3 means thousands have already passed unnoticed. That's why each detection is priceless. Unlike planets or stars, which remain visible for centuries, interstellar visitors give us only brief windows. Months, maybe a year or 2, then they're gone forever. Every photo, every spectrum, every measurement becomes irreplaceable evidence of alien star systems. The 3 known visitors each told a different story. Oumuamua was strange and silent, revealing almost nothing. Borisov behaved like a typical comet. But this new arrival was different, a cosmic exhibitionist. Within days, astronomers saw it releasing gas and dust, forming a glowing coma and faint tail as it neared the sun. Where Oumuamua was a locked vault, this comet was an open book. Its gases and dust carried direct samples of its alien origins. Spectroscopy revealed water vapor, carbon compounds, and organics, chemical fingerprints from a star system light years away. Unlike Oumuamua, which left us guessing, this visitor shouted its story. Its activity matched comet models perfectly. No mysteries, no strange accelerations, just predictable physics. Even better, we discovered it early, giving scientists months to study it as it brightened. Every molecule escaping from its surface was like a message from another world. Water vapor showed it formed in a cold, icy region. Carbon monoxide, carbon dioxide, and organics hinted at complex chemistry, possibly similar to the conditions that shaped our own solar system. These molecules are like cosmic DNA, carrying clues about temperature, pressure, and chemical reactions from a star system we may never see. For the first time, we had a detailed look at the raw ingredients of an alien world, delivered straight to our doorstep by a wandering giant. What made this discovery extraordinary was the clarity. Instead of faint signatures hidden in starlight, we had direct samples, gas and dust from another star system streaming past our telescopes. Each particle was a time capsule, preserved for millions of years in the deep freeze of interstellar space. Chemical analysis revealed something surprising. Radiation during its journey should have altered its makeup, yet much of the interior remained pristine, shielded by the comet's massive size. Some molecules showed traces of radiation damage, acting like cosmic timestamps, evidence of just how long it had wandered the void. Its path through our solar system seemed almost choreographed. Perfectly placed for months of observation, it avoided planetary encounters that might deflect it stayed visible without being lost in solar glare, and reached closest approach during autumn, prime observing season for telescopes worldwide. Scientists couldn't have asked for better conditions. As it neared the sun, the comet awakened. Ice that had been frozen solid for millions of years began to sublimate, turning from solid to gas. This process transformed the nucleus, a dirty snowball the size of a small city, into a spectacular display. Thousands of tons of material escaped each day, forming a glowing coma and twin tails, a blue one of ionized gas and a yellow one of dust. Every photo captured its ongoing transformation, each one documenting the release of ancient matter from a long-lost star system. Then came the sharpest image ever taken of an interstellar object, captured by the Hubble Space Telescope. Where ground telescopes saw only a fuzzy glow, Hubble revealed breathtaking detail. At the center, a bright nucleus glowed within its envelope of dust and gas. Streams of material flowed outward like frozen fireworks, creating a teardrop shape pointing away from the sun. Even more remarkable, Hubble caught active jets of gas bursting from the surface, fountain-like sprays marking regions where sunlight hit exposed ice. From these images, scientists estimated the nucleus to be 1 to 3 kilometers across, larger than Oumuamua, smaller than many local comets, but still monumental. More than just data, this was history. For the first time, humanity saw in stunning detail the material of another star system. Not just a comet, but a messenger, carrying the chemistry of an alien world straight to our telescopes. Trailing behind our visitor like a cosmic veil, its tail revealed secrets of both its past and present. Every glowing particle was once locked inside the nucleus for billions of years, now set free and scattered across our solar system. Spectroscopy showed distinct colors in the tail, blue from ionized gases, yellow and red from dust grains, each revealing the comet's composition. The rotating nucleus created spiral patterns, like water spraying from a spinning sprinkler, allowing scientists to measure its spin and map its active regions. The tail acted like a living fossil record. Older particles were pushed far into space by solar wind, while fresh material stayed close, creating a timeline written across millions of miles. Large dust grains hinted at rocky material, while tiny particles revealed fine dust from its birth in another star system. Most astonishing were organic compounds hidden in the dust, survivors of both its formation and its million-year journey. These molecules carried the chemistry of an alien world straight to our instruments. As the comet drew closer, 2 astronomical units from the sun, gentle heating turned into a cosmic blowtorch. Ice began to vaporize violently, blasting thousands of tons of gas and dust into space every hour. Radiation pressure pushed the particles outward, while jets of gas erupted like geysers, stretching for thousands of miles. Solar wind clashed with the expanding cloud, creating shockwaves that shaped the tail and produced spectacular sights, transforming an invisible speck of ice into a luminous beacon. By autumn, the comet faced its greatest trial, perihelion, its closest pass to the sun. At just 130 million miles away, it endured heat powerful enough to melt rock and metal. Telescopes watched as its coma ballooned larger than planets, outbursts flaring like cosmic explosions as buried pockets of ice erupted into space. This was the comet's moment of truth, like an ice sculpture racing through a blast furnace. Would it survive its fiery encounter, or vanish in the glare of the sun? For scientists, this stage was both triumph and tragedy. The comet was brighter than ever, offering priceless data, yet each day brought it closer to the sun's glare, when observation would become impossible. Its October passage would decide its fate, survival or destruction. To uncover its origin, astronomers turned to supercomputers. Reconstructing its path meant rewinding the motion of thousands of nearby stars, accounting for every gravitational nudge across millions of years. It was like tracing a single raindrop back through a hurricane. The results were staggering. Our visitor had been traveling for at least 4 million years, maybe much longer, covering distances so vast that even light would need decades to cross them. This wasn't just a comet. It was a time traveler, carrying material from an age when Earth's continents were still forming and life was only microscopic. Its survival was equally astonishing. Along the way, close encounters with stars could have torn it apart. Instead, it threaded a safe path through the galaxy, enduring the harshest conditions imaginable. In interstellar space, temperatures drop near absolute zero, where most matter becomes brittle. Cosmic rays bombard surfaces for millions of years, altering chemistry in ways unknown on Earth. Microscopic grains of dust slam into objects at incredible speeds, like sandblasting across interstellar distances. Yet this wanderer endured it all, arriving with its volatile ices still intact, proof of protective structures deep within. Each mile of its journey told a story of survival across cosmic ages. By the time it reached our telescopes, it was not only a comet but also a messenger, evidence that worlds beyond our sun create and send forth travelers capable of crossing the gulfs between stars. Most remarkably, the traveler had held together well enough to put on the breathtaking show we were witnessing. Every molecule of gas streaming into space was proof it had survived one of the longest, harshest journeys in the galaxy. Its speed, 36 kilometers per second, was more than just a number. It was a biography written in physics. Velocity is like DNA for interstellar objects, carrying clues about the violent events that launched them into space. Such speeds can only be achieved through extreme encounters, close passes with giant planets, gravitational slingshots around binary stars, or even the chaos of stellar explosions. The speed also revealed the kind of neighborhood it came from. Calm, stable star systems rarely fling out comets this fast. Our visitor's velocity suggested a birthplace in a dynamic, possibly chaotic stellar environment. Think of interstellar space as a highway system with different speed limits. Slow travelers usually come from nearby stars, while high-speed wanderers like this one may have crossed far greater distances from more exotic origins. Timing was another clue. Fast-moving objects crossed the galaxy more quickly, meaning this comet had likely been ejected within the last few million years, a relatively recent event in cosmic terms. By combining speed with direction, astronomers could rewind its path and search for potential parent systems. The challenge was immense. Even a measurement error of 1 meter per second could place its origin in an entirely different region of the galaxy. But velocity held yet another secret. Its trajectory pointed deep into the Milky Way's thick disk, a mysterious population of ancient stars that orbit above and below the galactic plane. These relic stars formed when the galaxy was still young, with far fewer heavy elements than newer stars like our Sun. The comet's chemical fingerprint matched this story. The ratios of elements in its ices didn't resemble local material from our solar neighborhood. Instead, they pointed to formation around a star with far fewer metals, exactly what we'd expect from the thick disk. In essence, it was carrying samples from one of the oldest stellar environments in our galactic backyard. Picture stellar neighborhoods as cultural communities, each with its own chemical signature. Our Sun's family is rich in heavy elements, built up by countless supernovae. But the thick disk is ancient, poor in metals, and tells of a time when the Milky Way was less than half its current age. This comet's ices had condensed back then, only to be flung into interstellar space by a rare and powerful event. Its unusual orbital characteristics fit this origin. Thick disk stars move in wide, elliptical orbits that increase the chances of dramatic gravitational encounters. Yet because these stars are so old and stable, ejection events are rare. For our visitor to have escaped, something extraordinary must have happened. An encounter violent enough to send this frozen messenger across the galaxy, only to arrive here billions of years later. Some scientists suggested our visitor may have been launched by extreme events, binary star systems slingshotting objects with their tangled gravity, or rogue planets and brown dwarfs crashing through stellar neighborhoods like cosmic wrecking balls. If so, and if it formed around an ancient thick disk star, this comet could be among the oldest preserved matter in our part of the galaxy, carrying fingerprints from an era when the universe itself was very different. Its ancient age wasn't only written in chemistry, but carved into its surface. For millions of years, cosmic rays, high-energy particles born from exploding stars and black holes, had bombarded it non-stop. Each strike shattered molecules, created strange new compounds, and slowly reshaped its outer layers. Over time, the surface became what scientists call space-weathered, covered in microscopic glass beads, metal particles, and radiation-damaged crystals. This damage acts like a timestamp, telling researchers how long it had wandered between stars. Think of it like erosion on Earth. Just as rivers carve canyons over eons, cosmic radiation sculpts interstellar objects on an atomic scale, leaving behind minerals and molecules found nowhere else. These altered layers also explain some of the comet's unusual behavior. Radiation damage can change how surfaces absorb sunlight, release gas, and reflect brightness, directly affecting the formation of its coma and tail. Spectroscopy confirmed this story, revealing molecules that could only have formed under intense cosmic ray bombardment. Some parts of the surface showed heavy alteration, while shielded regions remained more pristine. Together, this created a patchwork of activity zones that influenced where jets of gas and dust erupted as solar heating deepened. Ironically, the same radiation that scarred the comet also helped preserve it. The weathered crust acted as armor, slowing heat penetration and shielding the interior from micrometeorite damage. But as the sun's energy reached deeper layers, it began exposing pristine ices that had been sealed away for millions of years. If so, and if it formed around an ancient thick disk star, this comet could be among the oldest preserved matter in our part of the galaxy, carrying fingerprints from an era when the universe itself was very different. Its ancient age wasn't only written in chemistry, but carved into its surface. For millions of years, cosmic rays, high-energy particles born from exploding stars and black holes, had bombarded it non-stop. Each strike shattered molecules, created strange new compounds, and slowly reshaped its outer layers. Over time, the surface became what scientists call space-weathered, covered in microscopic glass beads, metal particles, and radiation-damaged crystals. This damage acts like a timestamp, telling researchers how long it had wandered between stars. Think of it like erosion on Earth. Just as rivers carve canyons over eons, cosmic radiation sculpts interstellar objects on an atomic scale, leaving behind minerals and molecules found nowhere else. These altered layers also explain some of the comet's unusual behavior. Radiation damage can change how surfaces absorb sunlight, release gas, and reflect brightness, directly affecting the formation of its coma and tail. Spectroscopy confirmed this story, revealing molecules that could only have formed under intense cosmic ray bombardment. Some parts of the surface showed heavy alteration, while shielded regions remained more pristine. Together, this created a patchwork of activity zones that influenced where jets of gas and dust erupted as solar heating deepened. Ironically, the same radiation that scarred the comet also helped preserve it. The weathered crust acted as armor, slowing heat penetration and shielding the interior from micrometeorite damage. But as the sun's energy reached deeper layers, it began exposing pristine ices that had been sealed away for millions of years. Yet, this discovery carried a sobering truth. For every interstellar visitor we catch, thousands more pass unnoticed. Most are small, dark, and frozen, nearly invisible until they skim close enough to a star to wake up and shine. By then, they're often already speeding away. Our telescopes can only skim limited slices of the sky, leaving huge blind spots. It's like trying to track traffic on a highway while peeking through a keyhole. We glimpse only a fraction of the cosmic flow passing through our solar system every day. Think of interstellar space as a vast ocean, with ships occasionally passing in the night. Most sail far from shore, unnoticed. Only the rare few that cross near us, or shine brightly enough, can be seen. The challenge is speed. An object moving 36 kilometers per second crosses our solar system in under 2 years. If spotted late, scientists may have only weeks to study it before it vanishes into the dark. New survey technology is changing that. Automated telescopes now scan huge portions of the sky, boosting our chances of catching these cosmic speedsters. Still, blind spots remain. Objects arriving from the sun's direction are invisible until they've passed, while others can hide in crowded star fields, blending into the background. The fact that we've confirmed only 3 interstellar visitors in history suggests many more have slipped by unseen. Each missed detection is a lost opportunity, unique data from alien systems that could reshape our understanding of the galaxy. But the 3 we have caught couldn't be more different. Oumuamua, our first, arrived as a puzzle, elongated, silent, with strange acceleration and no visible outgassing. It refused to fit any known category. Comet Borisov, the second, behaved exactly as expected. A textbook comet with a clear nucleus, glowing coma, and tail pointing away from the sun. Its chemistry nearly identical to comets from our own system. Now we face something entirely new, a true giant. Where Oumuamua was football field-sized and Borisov closer to a city block, this visitor stretches miles across. Such size hints at violent origins. Small fragments like Oumuamua may be gently ejected debris. Medium comets like Borisov likely formed during planetary system birth. But massive objects like our current guest suggest catastrophic upheavals in distant stars' neighborhoods. These 3 discoveries are like artifacts from alien civilizations, each revealing conditions in other stellar systems, each carrying the marks of survival through interstellar space. Their behaviors also tell different stories. Oumuamua stayed quiet, revealing almost nothing. Borisov showed modest comet activity, enough to confirm its nature. Our latest guest erupted into a dazzling display, releasing vast clouds of gas and dust that made it visible worldwide. Even their speeds offered clues. Oumuamua's modest pace suggested a nearby origin. Borisov's intermediate speed pointed to a more distant source. And the extreme velocity of our newest visitor points to chaotic, energetic regions of the galaxy. Each one not only expanded our knowledge, but also showcased the rapid progress in how we detect and study these rare cosmic messengers. Every molecule streaming from our visitor's core carried the chemical fingerprint of a world formed around another star. Spectroscopy acted like reading its autobiography, written in atoms and molecules. Each compound revealed details about the conditions where this object was born. Unlike distant exoplanets, where we only glimpse faint signals through atmospheres and starlight, here we had direct access to untouched material from an alien system. Water dominated the gases, but it wasn't like Earth's. Isotopic ratios showed differences in hydrogen, offering clues about the temperature and pressure when the ice first formed. These fingerprints worked like cosmic DNA, marking the birthplace of our traveler. Carbon compounds added another chapter. Carbon monoxide, carbon dioxide, and organic molecules suggested formation in a young star's debris disk. Locked in deep freeze for millions of years, they preserved the chemistry of a time when alien planets were just forming. The nucleus acted like a geological core sample, with layers recording different eras. As sunlight heated deeper parts, it exposed pristine materials shielded from cosmic rays for ages. The organic molecules were especially intriguing. They pointed to processes similar to those that shaped our own solar system. Their survival meant the parent system was stable long enough to allow complex chemistry to evolve. Even the metals told a story. Heavy elements in the gases hinted that the star had been enriched by past stellar explosions, much like our own Sunday. Some compounds showed evidence of cosmic ray processing during the journey itself. timestamps etched in chemistry, proof of millions of years spent drifting between stars. For the first time, humanity was studying matter forged in another corner of the galaxy. But time was running out. Across 6 continents, astronomers scrambled to capture every bit of light before the visitor slipped behind the sun's glare. Once hidden, it would reappear only to fade into the darkness forever. Observatory directors canceled planned projects. The Hubble Space Telescope, usually booked years in advance, was given emergency time. Ground observatories from Chile to Hawaii coordinated nonstop coverage. Even amateurs with CCD cameras joined the effort, filling gaps and confirming professional results. It became a global relay race. Optical telescopes tracked brightness and motion. Infrared instruments mapped heat and surface temperatures. Radio telescopes searched for emission lines that revealed the composition of its gases. Each observation was like a snapshot of a changing system. Outbursts sometimes boosted its brightness tenfold, but only for days before fading. The chase was complicated by Earth's orbit and shifting viewing angles. The geometry changed week by week, altering lighting conditions. Some measurements were possible only in narrow windows. Weather added more risk. Cloudy skies could erase irreplaceable data. Backup facilities in different regions became crucial. What haunted astronomers most was the knowledge that this might be our only chance. As this visitor raced towards solar conjunction, scientists were already planning for the next one. The European Space Agency's Comet Interceptor was designed for exactly that purpose. A spacecraft waiting at a stable point between Earth and the Sun, ready to launch at the moment another interstellar traveler is spotted. Unlike past missions that target known objects, this one will sit in ambush, ready to chase the next cosmic wanderer before it escapes. The idea marked a major shift in space exploration. Instead of chasing objects already fleeing the solar system, future missions would wait in position, ready to intercept visitors as they approached. Think of it like a Coast Guard station on a busy shipping lane, prepared to investigate any unusual vessel that passes by. This strategy required both patience and advanced technology. Spacecraft would need to sit dormant for years, then spring to life within days when a new target was found. They would also need enough fuel and maneuverability to reach objects with unpredictable paths and extreme speeds. The challenges were enormous. Traditional missions are designed for well-known targets with predictable orbits. Interstellar interceptors must be ready for anything: tiny rocky fragments, giant comets, or something in between. Payloads would include instruments to study surface chemistry, structure, magnetic fields, and escaping gases, packed into lightweight craft fast enough to catch interstellar wanderers. Timing added more pressure. From discovery to intercept, scientists might have only months to plan trajectories, upload commands, and execute complex maneuvers. Years of planning would need to be condensed into frantic weeks. Some concepts even included multiple spacecraft, one for a quick flyby, another to attempt a rendezvous. Together, they would maximize data and provide backup if one failed. The ultimate goal was to move from passive observation to active exploration, turning fleeting visitors into fully studied ambassadors of alien star systems. The rise of interstellar detections wasn't chance. It came from a revolution in how we scan the sky. 2 decades ago, spotting such objects would have been nearly impossible. Telescopes were built to study distant galaxies or nearby planets, not fast-moving specks racing through the outer solar system. The discovery of Oumuamua in 2017 marked the dawn of a new era. The breakthrough came from automated sky surveys that scan huge portions of the sky every night. Projects like Catalina, Linear, and Atlas replaced targeted observing with wide-field monitoring. Think of them as cosmic security cameras, photographing the entire sky repeatedly and comparing images to spot anything new or moving. Algorithms now sift through millions of data points each night, flagging potential objects for astronomers to check. This would have been impossible just 20 years ago. Today's computers can crunch the data in minutes. Modern CCD cameras are also far more sensitive, capturing objects thousands of times fainter than old photographic plates. That means surveys can now detect smaller, darker objects at greater distances. Global coordination adds even more power. When one observatory detects a candidate, telescopes worldwide quickly follow up to confirm and track it. New orbital analysis tools now identify hyperbolic paths, proof that an object comes from beyond the solar system. Thanks to this revolution, we now know interstellar visitors are likely common. They've always been passing through. We simply lack the tools to find them. The discoveries reveal that interstellar space isn't empty. It's a vast transportation network. Galactic gravity shapes invisible highways that guide ejected debris along predictable routes. Instead of wandering randomly, interstellar objects move like cars on cosmic freeways. Picture the galaxy as a giant city with highways, side streets, and intersections. Objects launched at certain speeds and angles follow these routes, passing multiple star systems along the way. Our solar system happens to sit at one of these intersections. Mapping these pathways means not only tracking current star positions, but also projecting where they'll be millions of years from now. Stars drift through the galaxy in complex orbits, constantly reshaping this hidden network of cosmic roads. Some routes in interstellar space appear busier than others. Binary star systems, with their tangled gravitational fields, tend to eject more material than single stars. Stellar nurseries, where young planets are still forming, also flood the highways with debris as leftover matter gets scattered. This helps explain why smaller rocky objects are far more common than giant comets. It takes less energy to fling out fragments, while launching massive bodies like our current visitor requires rare, violent events. Astronomers are now using these traffic patterns to refine search strategies. By tracking where these hidden highways cross our solar system, telescopes can be aimed in the right directions, raising the odds of spotting new arrivals. The ultimate goal is a complete map of interstellar transport routes, one that could guide future missions to intercept and maybe even ride these cosmic currents to other stars. What's emerging is a picture of the galaxy as an interconnected web, not a collection of isolated systems. We're entering a new scientific frontier, interstellar archaeology. Each visitor is more than just a comet or asteroid. It's a physical artifact from another star system, preserved in deep freeze for millions of years, now delivered to our doorstep. Unlike traditional astronomy, which relies on light from afar, this discipline gives us direct samples forged under alien suns. These wandering time capsules carry chemical fingerprints that tell us how planets formed elsewhere, offering ground truth for theories about solar system evolution. Imagine our solar system as a cosmic port of entry, with astronomers acting like customs officers inspecting cargo from distant neighborhoods. Every measurement adds another clue to the puzzle of galactic diversity. The archaeology analogy also fits the timescales involved. The objects arriving now began their journeys when Earth looked nothing like it does today. They carry echoes of an era when different stars lit our sky and the galaxy's chemistry was far younger. With next-generation intercept missions, we may not just observe these visitors. We could study them up close, return samples, or even land probes on their surfaces. This field also demands rapid response science and global teamwork. Because interstellar visitors are fleeting, astronomers must coordinate across observatories and agencies worldwide in real time, a scale of collaboration that has never existed before. These systems will prepare us for even stranger discoveries in the years ahead. Most importantly, interstellar archaeology is revealing that the galaxy is not a collection of separate islands. It is a connected ecosystem where material moves between stars, carrying chemical messages across vast distances. Our solar system is part of this galactic community, linked by invisible highways and ancient travelers. And as we learn to read their stories, we may uncover answers about how planets form, how stars evolve, and where life itself might find a foothold.